Okay, hi everyone. I got to say, this is great to see everyone here. Friday, Good Friday, before holiday weekend, the first really gorgeous day of spring, and I was a little worried that it was just going to be me and the cameraman here. So I'm really delighted to see everyone. Welcome to the second Future of Energy event of the semester. In April, we have now a kind of series of events packed in, so it'll be a very busy April. Today, I'll introduce our speaker, David MacKay, in just a second, but should note that on April 13th, we're going to have Christina Johnson here. Christina Johnson is the Undersecretary of Energy for Energy in the U.S. Department of Energy, and she'll be here. And then April 27th, Marvin Odom, who's the CEO of Shell America, will be here and giving a talk as well. So we're looking forward to both of those talks. And like all of the Future of Energy talks, this series is sponsored by the Bank of America, and we greatly appreciate their support that allows us to put on these events and distribute the talks on the web. You can all find this talk in a week or two, but then all previous Future of Energy talks over the last 4 years at environment.harvard.edu or energy.harvard.edu. Either will work. You will find the links to them. So it's my great pleasure to have David MacKay here today. David is in the Department of Physics at the University of Cambridge and studied natural sciences at Cambridge. He got his PhD at Caltech in computation and neural systems in 1991. Was a bit of an activist at Caltech at the time, at least for Caltech. He founded the Caltech Environmental Task Force and was involved in a variety of things in Southern California, is a fellow of the Royal Society, and a number of other distinguished things. But one of the things that really I think is so special about David is that he has successfully written a book for the broad public audience about the challenges of renewable energy that really, I think, interprets a lot of the science and technology very successfully for people who don't have a very strong scientific background. This book is called Sustainable Energy Without the Hot Air. It was published in 2008, and it's available free via download. Is that right? And so it's a wonderful thing. Recently, he was appointed the scientific advisor to the Department of Energy and Climate Change, and in that sense, he's actually on a complex coast-to-coast and back again U.S. tour discussing some of the challenging issues that his office is dealing with in that context. So please join me in welcoming David MacKay to Cambridge, or to our Cambridge.
Thank you. Thank you all for coming. This is a talk about visualizing life without fossil fuels. We have an addiction to fossil fuels, and it's not sustainable. When I say we, I'm talking about the so-called developed world. The developed world gets 80 or 90% of all its energy from fossil fuels, and living on fossil fuels for energy in this way is not sustainable for three fairly obvious reasons. First, on the left, easily accessible fossil fuels are a finite resource, and so at some point that resource will be exploited and humanity will have to do something else. Second, setting fire to fossil fuels puts carbon dioxide upstairs, so we have the climate motivation. The clear consensus of the climate science community is, with substantial error bars still on exactly what might happen, their advice is this is a geoengineering experiment that we're well advised to stop as soon as possible. And third, even if you don't believe in climate change, and even if global fossil fuels aren't running out today, it might be the case that your fossil fuels or our fossil fuels in a particular country or state have run out, and you might have to depend on other countries or states for fossil fuels in the future. So you have a security of supply motivation for saying, let's look into really getting off fossil fuels in a serious way. I find all three of these motivations equally compelling, and I'm just going to take it as given now that we are interested in discussing life after fossil fuels. So everyone gets rather emotional when we get into this topic of what to do about our energy system. And when I wrote my book about sustainable energy, I was trying to help. I'm sure emotions are important, but we also need facts and numbers. And I tried to write a book that would be agreed by everyone as having useful numbers, approximate numbers for constructive conversations about energy options. The point is it's not actually going to be easy to get off fossil fuels. So I'd like to offer you a rough guide to sustainable energy with deliberately inaccurate numbers, deliberately inaccurate so as to make them easy to remember. I'm going to try and avoid talking about any numbers that come in millions, billions, or trillions, because I think few people actually understand the difference between those sort of quantities. Even thousands are just very big. So let's do our calculations per person, and I suggest these units for discussing energy: kilowatt hours. Your electricity meter at home reads in kilowatt hours, I suspect, and maybe your utility bills come in kilowatt hours, and many everyday choices that you make come in small numbers of kilowatt hours. That's why I like it as a unit. It means the answers will come out in 3s, 5s, 10s, and 50s. If you switch a 40-watt light bulb on for 24 hours, you use 1 kilowatt hour of electricity, and maybe it costs you 10 or 15 cents. If you eat food, the chemical energy in the food you eat amounts to about 3 kilowatt hours per day. If you take one hot bath, the heat energy in the bath is 5 kilowatt hours. If you take a litre of petrol and set fire to it, that dissipates 10 kilowatt hours of chemical energy. If you have a Coke habit and you drink Coke and throw away Coke cans, the embodied energy, the energy required to make the aluminium in that can that is so easy to throw away, is about 2/3 of a kilowatt hour. So there's some everyday choices that come in on 1 or 2 hands worth of kilowatt hours. Other choices involve larger numbers of kilowatt hours. If you drive an average European car 100 kilometers, you use 80 kilowatt hours. If you make the decision to make a return trip between continents, say from London to Los Angeles and back, then you use an incomprehensible number, 10,000 kilowatt hours. That's the passenger's energy footprint for that single decision. To make it comparable with other things, let's talk about how fast we use energy and describe energy use per day. If you go to London and Los Angeles, from London to Los Angeles once per year, your average rate of using energy for flying is 26 kilowatt hours per day. So that's back in the same ballpark as the 80 kilowatt hours per day for the person who decides to drive 100 kilometers every day. Similarly, running a house, we can express in kilowatt hours per day how fast we're using energy. This North American house uses 80 kilowatt hours per day of electricity. Running the cat in the front garden requires an extra 2 or 3 kilowatt hours of chemical energy. And other examples of things that use energy can all be expressed in the same units. Here's a poster from a London campaign to raise awareness of saving the planet by small lifestyle changes. And you can see unplugging your phone charger is recommended as one of the 7 things that people should be paying attention to. If every London household unplugged their cell phone chargers when not in use, we would save 31,000 tons of CO2 and millions of pounds per year. So here we have thousands and millions. Clearly, these planet-destroying black objects are about as evil as Darth Vader. And so let's just pin down the numbers in a single set of units. The energy saved by the feat of switching off the phone charger for an entire day is, well, the phone charger is dissipating a half a watt, in fact. So you add it up for a whole day. The energy saved is the same as the energy used in driving an average car for 1 second. Both of them are equal to 0.01 kilowatt hours. Now, I'm not saying don't switch off the cell phone charger. Do switch it off. It will save you $1 or a pound a year. But is this the number one thing we should be talking about? Or is it in the top 7 things we should be recommending to people? I suspect it really deserves to fall low down the list of priorities. And we need to improve our public communications to get people to prioritize actions that really make a difference. So these are examples of energy consumption choices we can make. When we look up national statistics and divide the total energy consumption by the number of people in the country, we find for a typical European country like Britain that the consumption is 125 kilowatt hours per day per person. And that's also the European average energy consumption. You can visualize this in various ways. One way is this is like every European having 125 light bulbs on all the time. That's the same as the modern Europeans' energy consumption. Americans use, on average, taking the entire energy consumption, sharing it between 300 million people, 250 light bulbs each, 250 kilowatt hours per day per person. Where's this going? Well, in Britain, it's going into transport, heating, especially hot air for buildings and also hot water, and other stuff, much of it being electrical consumption. So for a quick conversation of where does the energy go, what can we do about it? Transport, heating, electricity are the top 3 things to consider. When we talk about getting off fossil fuels, one of the prominent options is renewable power sources, and when we discuss those, most renewables involve doing something on a piece of land or possibly a piece of sea, and we need to talk about how much power you can gather per unit area from those. And the units in which I'm going to measure powers per unit area are going to be watts per square meter. Incidentally, you will have already noticed I'm measuring power, which is how fast we use energy, in kilowatt hours per day. 1 kilowatt hour per day, remember, is the same as 1 40-watt light bulb. And the physicists and engineers in the audience will be spitting at this point and saying, why is he using kilowatt hours per day? What an ugly, horrible unit. Why doesn't he just use watts? Well, there's a couple of reasons. One is the watt is too small, and the kilowatt is too big a unit for the answers to come out in 5s, 10s, and 20s. And secondly, I think people don't understand watts. If I tell you the average European uses 5 kilowatts, I think many people might say, is that kilowatts per month or per year? So people don't actually know that a watt has got the per time built into it. By saying kilowatt hours per day, yes, it's ugly, but it has the time explicitly there. So people understand we're talking about a rate. But for powers per unit area, I'm going to use the SI unit, watts per square meter. We need to talk about population densities as well, because we need to know how much area each person has to harvest renewables from if we want renewables to make a substantial contribution. And the population density of the UK is 250 people per square kilometre. The population density of Massachusetts is also 250 people per square kilometre. So everything I say about the UK applies to Massachusetts as well, if we're trying to visualize life without fossil fuels for a state like Massachusetts. The population density of the USA as a whole is significantly lower. So the answers depend on which contiguous region, which country or state we're talking about, what the visualizing of life without fossil fuels will actually look like. For Massachusetts and for Britain, the area per person is 4,000 square meters. That's the area of half of a Premiership football field for each person. So let's now look at a map of the world. This is a map of the world where the horizontal axis is showing population density, which I just mentioned. For Britain, it's 250 people per square kilometre. And energy consumption per person is on the vertical axis, and that's 125 light bulbs per person for Britain. This map shows European countries over hereabouts. And African countries are in blue down here, and up in the top left we have countries with very low population density, Iceland, Canada, Australia, but very high per capita consumptions up in the 200 or 300 light bulbs per person area. Both of these scales are logarithmic, so as I go from this line to this line, it's a 10-fold increase in population density, and the same when we go up to here, another factor of 10. So Bahrain's population density is more than 100 times greater than that of Iceland, but its energy consumption per person is just the same. Coming back down here, we go down 2 factors of 10 in energy consumption to Bangladesh, where people just use 3 kilowatt hours per day per person, and they have the same population density as Bahrain. Over in the bottom left, there used to be countries over here, but they're all rushing up and to the right to come and join us in the top right-hand side of this diagram. This next rendering shows you a few tails behind showing progress. This is 15 years of progress from 1990 to 2005. Every country has a population density that's increasing and an energy consumption that's increasing. They're all going up and to the right. This is the world average, moving up and to the right, just crossing over 0.1 watts per square meter. What are these purple lines? Well, the advantage of using logarithmic scales for these 2 diagrams is if you multiply the energy consumption per person by the population density, you get the power consumption per unit area of the country that we're talking about. All of the countries on this line here are using 0.1 watts per square meter. That's their power consumption per unit area. That's the world average. It's the same for Jordan, for Saudi Arabia, and it was the same for Bangladesh in 1990. The UK has a higher population density and higher per capita consumption than the world average, and it's using 1.25 watts per square meter. Here's America with higher per capita consumption, lower population density at something like 0.3 watts per square meter. Why is this useful? Well, as I said earlier, renewables many of them have a power per unit area as well, and we can put that into exactly the same units so we can understand the scale of what's involved if we want to visualize a renewable-dominated future, or a future in which renewables make a significant contribution. What I've done between these two pictures here and here is I've shrunk the diagram down a little bit to the left, and I've added some green lines. So now Bahrain is in the top right over here, and we have lines showing the power per unit area of various renewables. Wind power, for example, delivers in a windy location roughly 2.5 watts per square meter, which is twice the power per unit area that Britain is currently consuming. So the message from this is, if half of Britain were occupied by wind farms, then the output of those wind farms, on average, would equal our average power consumption. And some people might view that as a slightly intrusive change to the countryside of Britain. And Massachusetts, we have the same rough message, that if half of Massachusetts were occupied by wind farms, that set of devices would match.
It's not windy enough.
And maybe it's not windy enough, and maybe the per capita consumption is slightly higher, so actually maybe you need slightly more than half of Massachusetts occupied by wind farms, or an area in a windy location similar to the area of Massachusetts. Okay, so, and I've got data to back this up from British wind farms in windy locations. They vary, and the mean is roughly 2.5 watts per square meter, including onshore and offshore wind farms in the British Isles. Some people think I'm being anti-wind by saying this. I'm not anti-wind. I am actually pro-wind, and I'm especially pro-arithmetic. And I just want us to have honest numbers where we really visualize what needs to be done. But perhaps talking about half of a country being occupied by wind farms is a negative way to put things. Let's put it another way. Let's personalize what we're talking about and imagine a community of people making a decision. Let's imagine not trying to get a full 125 light bulbs per person from wind, but just getting, say, 17 kilowatt hours per day per person, which is the UK's average electricity consumption. Note, energy comes not just in electricity, but in other forms for transport and heating and so forth. Let's aim for 17 light bulbs per person. What community decision do you need to make? Well, 700 people could make the decision to own one of these enormous cathedrals of architecture, one 2-megawatt turbine. And if the 700 people join hands around that turbine, that's an accurate visualization of the potential of wind. Wind farms do work, if they're located in windy locations at least, and the output of that turbine, on average, would be the entire electricity consumption of those people. So I think there are positive ways to visualize wind turbines, and perhaps the public attitude to wind farms can be transformed. Next, let's talk about energy crops. Energy crops in northern climates deliver something like half a watt per square meter. Here's miscanthus, which is a famous new energy crop people talk about, and here's some data on real productivities of various energy crops. These ones are in northern climates. In tropical climates, you can get more from the C4 crops as long as you apply fertilizer and irrigation. But a ballpark figure of half a watt per square meter implies that even if you cover the whole of the UK or the whole of Massachusetts with the best energy crops, you still can't match the power consumption of that region. That message doesn't apply to Brazil. Brazil can cover a fraction of itself with energy crops and power itself if it wants to. So the answers are different for different countries. Here's some more renewables, and the message for all of them is, much as I love them, they are all diffuse. They all have a small power per unit area, similar to that of the wind farms with which we started. Solar panels on roofs, for example, deliver something like 20 watts per square meter in Britain. Britain's not the sunniest place, so you could get more if you put them in a sensible place, such as India or China, or Africa, indeed. And Arizona is also obviously a good candidate. But 20 watts per square meter is the actual output of these solar panels in Britain, which means if you cover all south-facing roofs in Britain with solar panels, what you would deliver is about 5 light bulbs per person of power, which is quite a substantial amount. It shows up on the scale that goes up to 125 light bulbs per person, but it's only that much. And so if you're really wanting solar to make a huge contribution comparable to our total consumption, we need to go a little bit crazy, leap off the roof and do what the Germans do. Here's the traditional Bavarian farming method, where you coat the countryside with solar panels also. Spacing them apart with gaps in between and avoiding shadows means that the power per unit land area is reduced to 5 watts per square meter. That's just twice as good as wind farms in terms of power per unit area. In terms of cost, this is a lot more expensive than wind farms. So the message is still a roughly country-sized area would have to be occupied if you want to match today's consumption. Next, tide pools are a possible technology with places with big tides. There's a tide pool on the east coast of England here that's been there for 800 years. You let water in, you let it out at low tide and get something to go around. And the power per unit area of tide pools, here's an example in France, a rather larger modern tide pool. The power per unit area is about 2.7 watts per square meter, much the same as wind farms. So straight away, we know the message. The message is, if you want tide pools to really make a big contribution, you need a tide pool not the size of a small estuary, but you need a tide pool roughly the size of a country. And God, in his wisdom, when he created the British Isles, provided us with exactly such a facility. It's called the North Sea. The North Sea is an enormous natural tide pool, in and out of which and around which great sloshes of energy pour every 12 hours. And here on the map in yellow are shown the places where the natural currents are already very big, and we could exploit those natural flows by putting something that goes round into those yellow spots. Indeed, lots of underwater windmills, such as this one which has recently been launched in Northern Ireland. Many of those, thousands of them, tens of thousands, could be deployed in these yellow spots. What's the power per unit area? Well, something like 8 watts per square meter is my estimate of what these underwater wind farms could deliver. So perhaps 3 times as good as an above-ground wind farm. So we're still in the same ballpark. Perhaps a 1/6 of a country-sized tide farm would match today's power consumption. Next, let's talk about hydroelectricity. The power per unit area of rainfall arriving at ground level in British Highland areas is about 1/4 of a watt per square meter. So you need a very large catchment area to get anywhere near today's power consumption. In Britain, the hydroelectricity was originally developed there, but now it delivers about 0.2% of our total energy consumption. Concentrating solar power in deserts delivers about 15 or 20 watts per square meter. Here's a photograph of some beautiful concentrators being developed, I believe, in America. Of course, Britain and Massachusetts don't have any deserts yet. But let's look at them anyway. Here's a prototype in Spain which will use molten salt which can be stored at night so as to generate solar power at night as well as during the day. This facility is predicted to have a power output of 10 watts per square meter when it's finished. This one delivers 5 watts per square meter. And here's another device using concentrating solar power onto photovoltaics, delivering, this single device delivers 140 kilowatt hours per day. The Americans' total energy consumption is 250 kilowatt hours per day per person, so you need slightly more than one of these objects per person if you want to match today's power consumption. That's power in all forms, electricity, transport, heating, the lot. And here's a person for scale. Here on the next picture is a former American president for scale alongside one of these Stirling engine devices, which are equally large and have a very similar output. Again, 160 light bulbs is the average output of one of these things. So let's keep on all the options on the table until we've got ourselves a plan that adds up. The message about the renewables is to make a difference, renewable facilities do have to be country-sized. And you could say, oh, I'm going to have a diversity. I'm not going to focus just on solar. I'll have a mix. Well, no problem. They all have roughly the same power per unit area, so the total area occupied still has to be the same as what we were just talking about. We're talking about roughly half of Massachusetts, roughly half of the UK is the ballpark area that we need to imagine if renewables are going to add up. And there's some people in denial over this, saying they don't like intrusive renewable facilities like the Severn Barrage proposed for the estuary in Britain. And I don't understand what the less striking measures are that they have in mind. Well, maybe they're right. They say less striking measures would cost less and could do more to cut carbon emissions. Well, if all they want is a 1% cut in carbon emissions, then they're absolutely right. You get everyone to grasp the thermostat and rotate it to the left 1 degree in the winter so that we don't heat our buildings quite so much. That would give a 1% cut in carbon emissions too. But do we just want a 1% cut in carbon emissions? If we're serious about getting off fossil fuels, we presumably are interested in 90% cuts. That's what the climate scientists are asking us to achieve by 2050. So I'm sorry, we need to keep some of these intrusive options on the table until we've got the plan that adds up. It could be that the RSPB, when they were saying they want less striking measures, it could be that what they had in mind was actually nuclear power. Nuclear power, in terms of its intrusiveness, in terms of the area required for a nuclear source, is much less intrusive. Here's a 1 kilometer square on a map, and it's got a Sizewell B inside it. Sizewell B is a 1 gigawatt power station, and so we have a power per unit area of 1,000 watts per square meter, which is 400 times better than the wind farm. Of course, this is not the only metric we should be using in comparing power sources. There are other considerations, there's cost and risks and so forth. But in terms of area occupied, nuclear facilities do have a higher power density. Now, we live in democracies, and in democracies, at least in Britain, we have to have consultation exercises when we imagine building new energy infrastructure. And here's a photograph of a consultation exercise in full swing in the little town of Pennacook, just south of Edinburgh. And you can see the children of Pennacook celebrating the burning of the effigy of the wind farm. Because if there's one thing the British people are good at, it's saying no. And here's just a few more organizations expressing their opinions. So, there is a public difficulty not only with nuclear but also with wind, and that's summarized on this map, which shows in white the places that are too near to human habitations, therefore ruled out because of disturbing humans, and in black the regions which are more than 2 kilometers from a human habitation, and therefore these locations are tranquil, and we can't go spoiling tranquil locations with wind farms, can we? So anywhere that's not black or white on the map is fine. Now, you might say, oh yes, of course, we'll put them offshore because no one objects to offshore wind farms, do they? But here's Save Our Scenery, and here's people worrying about threats to airports, threats to surfers, fishermen, and the military who can't defend us because the radar won't work anymore when we have wind farms in the sea. So all of those constraints cause great difficulties and perhaps rule out most of the areas where you would like to have wind farms. You wouldn't have any such problems over here, would you, in a rational country? When you discuss your wind options, well, a couple of years ago there were a few people having lively conversations about Cape Wind. So, what's the big picture? The big picture is countries in the top right-hand side of this diagram will truly struggle to power themselves solely on renewables, especially if we can't transform the public attitude to renewables. What should we do about that? Well, there's various approaches. One is to politely ask countries at the top left of this diagram, like Australia, Canada, and Libya, you have plentiful renewables per person, so please could you export to us some of your renewables that we don't want to build in our backyard. Another approach would be to look for other ways of moving this dot, perhaps down and to the left again, or to look at other sources of supply in addition to renewables. So here's what I'm imagining you might be able to get. This is a comparison of our 125 light bulb habit today with what we might be able to get from renewables without huge public objections. How can we make a plan that adds up? Well, we can do something to the demand, and we could do something else to the supply. So on the demand side, we could reduce population to bring ourselves back down. I don't know how to do that in a friendly way. You could ask people to change their lifestyle so that they don't use so much energy. You know, use less transport, less heating, buy less stuff, throw less things away, become vegetarian, and so forth. But I become a bit terrified of suggesting lifestyle when I encounter people whose off-road driving consists of parking on the grass on the verge of the road in a car that has teeth. So my strategy when I present the numbers is to say, well, let's leave lifestyle change on the table just off to one side, and let's discuss everything else we can do and see if we can make a plan that adds up, that is to our liking. And then we can always bring the lifestyle change back in at the end of the conversation if we feel like it. So I'm not forcing any recommendation on anyone. Let's just see if we can make a plan that adds up. What are the other ways of reducing demand? Well, technology. Boston's a famous home of technology innovation. And isn't it possible to just solve everything with wonderful technology that's more efficient and allows us to have the same lifestyle but use far less energy? Let's think about that. Then on the supply side, our supply side options could include clean coal, which means let's carry on using fossil fuels after all, but do something better with the carbon dioxide. Nuclear power, which is another fossil fuel with various popularity problems. And finally, the option I mentioned earlier of politely asking another country or another state, such as Arizona, please can we have your renewables because we don't want ours. So let's talk through the efficiency and technology options very quickly using a cartoon of consumption that says it's going into transport, heating, and electricity. How do we make transport more efficient? Well, here's the 5 physics principles we need to apply. Transport uses energy for various reasons. If you make your vehicles have small frontal area per person, that reduces the air resistance. If you have a vehicle with small weight per person, that reduces rolling resistance and braking losses. If you can get your vehicle to convert energy efficiently from one form to another. Incidentally, petrol and diesel engines are only 25% efficient at turning chemical energy into oomph. If we can convert energy more efficiently, then we're going to be more efficient, obviously. Fourth, go slowly to reduce air resistance and braking losses. And fifth, go steadily to reduce the braking losses. So we take all these 5 physics principles. We start from an average European car using 80 kilowatt hours for every 100 person kilometers it generates. That's if it's singly occupied in the traditional way. Apply all 5 principles, and we end up with a new piece of technology called the bicycle. This is powered by biofuel, by Wheaties, and it uses 1 kilowatt hour per 100 person kilometers. That's 80 times as good as the fossil fuel vehicle we started from. But the lady in the tank on the left will say, no, that's a lifestyle change. I can't possibly ride a bicycle. I demand a steel box to zoom in. So how about zooming in this? Here's a piece of public transport using 6 kilowatt hours per 100 person kilometers. That's more than 10 times as good as the fossil fuel vehicle. But the lady in the tank on the left will say, no, that's a lifestyle change too. I can't possibly travel with all those horrible people. So you have to have your own personal box to move in. Well, how about zooming in this? This eco car comfortably accommodates 1 teenager. It is almost as good as the bicycle in terms of its energy consumption, and it's shorter than a traffic cone. And it delivers this performance as long as you don't go faster than 15 miles per hour. So this is the possibility for innovation using a fossil fuel vehicle that's smaller. And the lady in the tank might say, no, that's no good either. So can we give us something that's more familiar, a vehicle that looks like a car but uses less energy? Well, you can't do much about the air resistance. If you zoom along, you create swirling air behind your car, except you can make it more fish-shaped like this one on the right. But the biggest saving perhaps comes from electrification. Petrol and diesel engines are 25% efficient at turning chemical energy into oomph. In an electric vehicle, you have a battery that contains chemical energy, and through the miracle of chemistry, you end up with oomph at the wheels with an efficiency of about 85 or 90%. So electrical vehicles are far more energy efficient. Here's one in London whose energy consumption is 21 kilowatt hours per 100 kilometers. That's measured at the socket. And you might object and say, well, where did that electricity come from? If the electricity came from fossil fuels at a power station that's only 30% efficient, then of course we haven't gained very much by this innovation. But we don't have to get our electricity from burning fossil fuels. There are other ways to get electricity. Wind farms, underwater wind farms, nuclear power. So there are other options that we can be looking at. And electric vehicles aren't new. Here's Edison with an electric vehicle, and here's a French world speed record holder in 1899 in an electric vehicle. And there's lots of them being developed now, and they all have performance similar to the one that a friend of mine measured at the socket with that London car. Here's some muscle cars that look quite promising. And here's some with crazy doors, which do even better, with consumptions of just 6 kilowatt hours per 100 kilometers. Electric scooters are even better, coming in at 3 kilowatt hours per 100 kilometers. And as a transitional technology, plug-in hybrids offer us a way to carry on using a little bit of fossil fuels and wean ourselves onto electric vehicles without feeling too uncomfortable. A plug-in hybrid would have a little petrol or diesel engine on board that can recharge the battery if you start running out of juice, and thus give you a range similar to a standard fossil fuel vehicle, while actually most of the time behaving like a standard electric vehicle. I don't understand why, but there seems to be an obligation that all plug-in hybrids have to look like killer robots from the future. And what's their performance? They use about 25 kilowatt hours per 100 kilometers. So not quite as good as the electric vehicles we just saw because of the extra weight, presumably, but promising nonetheless. Okay, so electrification is a technology that allows us to make transport much more efficient. What about heating? Why do we need 40 kilowatt hours per day of heating in cartoon Britain? Well, it's mainly because we have crappy buildings. And here's a crappy building in Cambridge. It's my house with the Ferrari out front. And it loses heat because it's leaky, and there's a temperature difference between the inside and the outside for much of the year. And the heat loss is the product of those two terms. And the power required to make up for the heat loss is the heat loss divided by the efficiency with which you can create heat from your power source. That's called the coefficient of performance of heat creation. And for setting fire to natural gas, which is a standard method of making heat in Britain, the efficiency is about 90%. And that might sound quite good, 90% from chemical energy to heat. But in a moment, I'll show you that this is not very good and we can do much better. How do we reduce the power required? We attack the three colored terms on the right-hand side. We can reduce the temperature difference with this amazing piece of technology called the thermostat, which I mentioned earlier. You can turn your thermostat down 5 degrees. It will halve your heating consumption. I've tried it. It works. And some people call it a lifestyle change. Second, we can reduce the leakiness. This can be done by putting fluff in the walls, fluff in the roof, and perhaps getting a new front door with better insulation properties. All of these measures might give you a 25% improvement. What's really needed to significantly reduce the leakiness is either the Swedish method of bulldozing the British house and building one to good quality Scandinavian standards, or we could go for the German retrofit technique where you actually put 12 or 20 centimeters of rock wool on the outside of the walls to really improve the insulation properties of the building. What else can we do? Well, we could make the heat delivery system more efficient. 90% sounded pretty good, but the important news is that there are ways of delivering heat into buildings that are far more efficient than 90%. 90% efficiency at turning high-grade chemical energy into low-grade heat is actually not at all good. Heat pumps, which are back-to-front refrigerators, are a way of delivering possibly as much as 4.9 units of heat for every 1 unit of chemical energy, of electrical energy, high-grade energy, that the heat pump takes. So here in Japan, they've recognized the importance of heat pumps for several decades, and they've had an efficiency drive that says all heat pumps must be better than average, and the results are here. You see Pumpu and Tankman both with cape and gloves, and they've got cute eyes, the lot. They're amazing. So Pumpu is an air source heat pump. He pumps heat like a back-to-front refrigerator, moves heat from the garden into the kitchen. And you give him 1 unit of electricity, he ends up delivering 4.9 units of heat into the kitchen and into Tankman, who's a hot water container. So, are heat pumps really this good? Perhaps a coefficient of performance of 300% is realistic for heat pumps. If anyone here knows more about them and has good data for their performance in North America, I'd be very interested. There are various flavors of heat pumps that can pump heat from the air, like Pumpu does, or you can pump heat out of the ground using ground source heat pumps. And so if a building is currently not being heated with a heat pump, perhaps we can make things far more efficient by switching to heat pumps. A final thing to say about possible efficiency measures is there's this astonishing technology called read your meters. And this has had the biggest effect on my life of all the technologies I've tried. I was writing a book on sustainable energy, and a friend asked me, how much energy do you actually use at home? And I was embarrassed to say that I didn't actually know. I had the meter readings, but hadn't been looking at them. So I started reading my meter every week. And I used to use 40 or 50 kilowatt hours per day of natural gas to warm the house. And after reading the meter every week, I ended up using 13 kilowatt hours per day. So this is about a 60% saving in energy consumption for heating. Excuse me. And similarly, I was reading my electricity meter every week, and doing that reduced my electricity consumption from 4 kilowatt hours per day down to 2 kilowatt hours per day. So what's going on? Well, by reading the meters, you start playing a video game, you become a scientist, you do experiments, you wonder, can I beat last week's high score? And you try things out. I attended a talk where someone said the average temperature in British buildings used to be not 20 centigrade in the winter, but 13 centigrade, 7 degrees centigrade lower. And so I thought, well, let's try it. And the fact is, if you've just cycled in on a freezing cold night, you come into a building at 13 centigrade, it feels perfectly warm, at least for the first hour or two. And if you're only in there for an hour or two, then there was no need to warm the building at all for the whole day before you got home. And so I think thermostats are wrong. We shouldn't have thermostats where you set a temperature. One thing that's wrong with this thermostat is it doesn't have any way of switching it off. This is my hotel room in Boston, and it right now is carefully pinning the temperature to whatever the thermostat is set at. There's no way I can tell it. I'm not actually there. So we've got to get away from thermostats and get people tinkering with their environment. Here's the experiments I did on electricity consumption. For a few days I lived normally, and then I tried doing the experiment of switching off all the vampires, not just the phone charger, which we know is not very important, but the DVD player, the stereo, the modem, and all these things that I wasn't using most of the time. I tried switching them all off, and I found that my background consumption went down from 70 watts to 25 watts, which is a saving of 1 kilowatt hour per day, 1 light bulb's worth, so worth doing. It's about 1% of an average person's footprint. And this saving of £45 a year, of course, I can spend on an extra holiday in Lanzarote. Which brings us to Jevons paradox, which is to remind you that we can make technology more efficient and feel very good about that, but perhaps the outcome of these efficiency measures is you actually end up using more energy. So that's something to worry about, and I don't have a solution. Okay. I've talked through the technology and efficiency options. Now what about the supply side? Well, I've mentioned 3 options there. Maybe I need to move on. Let's talk about how to make a plan that adds up. There's one more detail that we'd better talk about. It's not enough to have average demand match average supply. We need them to match all the time, and perhaps that requires demand management and some storage mechanisms. So I'd like to say a little bit about storage. In Britain, electricity demand currently fluctuates every day. These are daily fluctuations. And gas demand for heating varies annually. This is 1 year's variation with great big spikes when the temperature is low. These are temperature graphs up here, and this is gas consumption going up into the 76s of kilowatt hours per day per person nationally, compared with a summer consumption of 32 kilowatt hours per day per person. So we have fluctuations, and we need to cope with them in some way. And on the electricity side, storage systems are an option, pump storage systems like this one in North Wales. And heat storage, I think, is going to be a very important technology for this 2050 future that we're trying to visualize. If we can move heat, if we can have heat do time travel from summer to winter, that could really help out with the midwinter peak demand. And in Canada, there's a solar community where 50 homes are using extremely outsized solar hot water panels on their garages here to generate far too much hot water in the summer, and they pump the heat down into the ground and then pump it back out in the winter. So here's the hole in the ground, lots of holes 35 meters deep in a place with a radius of 35 meters or so, which has very much the same scale as the ice houses that used to be common around this part of the world. And it's got a similar function. This was for time travel of cold from winter to summer, of course. And there indeed used to be an international energy trade transferring cold on ships around the world. Norway used to export ice to London to the tune of 340,000 tons of ice per year. Okay, how do we make a plan that adds up? I'm suggesting largely electrifying transport, largely electrifying building heating using heat pumps, and insulating all buildings as well as possible and engaging people with reading their meters are some key actions to take on the demand side. Then we will probably have a roughly tripled increase in electricity demand because we've electrified transport and heating on top of what we're already doing. This is assuming no radical lifestyle change. So how do we satisfy the tripled electricity requirement? Well, the mix will have to involve our renewables, nuclear power, which might just be some sort of stopgap, clean coal, again, unproven at scale, possibly just a stopgap, and finally, other people's renewables. So how can we put these options together? Let's assume that we do have a tripling of electricity supply. This map visualizes for the UK what you could build in order to match a tripled electricity demand. And it's got a diversity of options. I'm not recommending this particular mix. I'm choosing a diversity because it allows you to visualize very easily the exchange rates and the alternatives that we might want to choose after looking at this map. First on the list, let's have solar power from other people's deserts. We're getting 16 light bulbs per person from Libya or Algeria. I visualized to scale on this map the size of those facilities. They're roughly twice the size of London in the Sahara that you would need. And in addition, there would have to be power lines all the way across Spain and France, delivering the power from the Sahara to Surrey. The next thing on the list by size is nuclear power. Here I have 16 kilowatt hours per day per person of nuclear. This would correspond to a 4-fold increase in nuclear over today's levels in Britain, which could be accommodated at most of the sites where we have nuclear power, as long as we had 4 power stations per location. Next, on the renewable side, the biggest renewable I'm showing here is wind power. Each of these grey squares shows to scale 100 square kilometres of wind farm, some of them in the sea, some of them in England, and some of them up here in Scotland. In fact, lots in Scotland, because Scotland currently is anti-nuclear, and that's no problem. You just get more wind farms. And this visualization shows the exchange rate. If you say, no, I don't want solar power from someone else's desert, no problem. We cross off the yellow block and we say, oh, we just need twice as much nuclear power as we had a moment ago. So we need an 8-fold increase in nuclear power over today's levels. And we still have a plan of the same type. Or you could say, no, I don't like nuclear power. So we cross off the nuclear and we could say, let's have more wind. So you just need 3 times as much wind as is shown on this map here. So this is an illustration of the scale of action that's required. Let's just reflect on where we came in. People often say, solar power is huge, there's far more sunshine hitting the Earth than humanity consumes, so we can easily live on solar power. This is technically true. This yellow square shows if everyone on this map, if 1 billion people in Europe and North Africa wanted to have a European level of energy consumption entirely from solar power, this yellow square could deliver that to them. You fill this yellow square with concentrating solar power, and everyone could have 125 light bulbs of power. And this square is sometimes said to be a very small square because it's so much smaller than the Sahara Desert, but it is the same size as Germany. And there's a similar message in the United States and the rest of North America. If you wanted to power the 500 million people of Canada, Mexico, and the USA, all at the Americans' current standard of living of 250 kilowatt hours per day per person with solar power alone, then you would need a solar facility of just the same size, a Germany-sized one, which is slightly smaller than Texas. And you could say, well, don't be silly, we don't only want solar. Well, I agree, you could have a mix, but if the mix includes other renewables, the square only gets bigger. So what we need to be visualizing for America, if we want to make a plan for getting off fossil fuels, is even with all the efficiency measures that we were discussing earlier, we need to be talking about wind farms the size of California, about solar power stations the size of Arizona, and about nuclear power stations increased 5-fold over today's levels. That's an example of a plan that might add up. In conclusion, getting off fossil fuels is not going to be easy, but it is possible, and it may even be fun. Thank you very much for listening.
We have a couple of microphones here, so if people would like to ask questions of David, please hold up your hands and we'll try to accommodate many of you. Down here, please, first. Wait for the microphone, because that way we can get it on videotape.
Yeah, can you comment on the role of how much energy it costs to create a Texas-size bank of photovoltaics and how that enters into the equation?
Okay, what's the energy cost of making these sort of things? Solar facilities in other people's deserts, wind farms, nuclear power stations. Did I include that in my calculations? No, I just assumed they were free things. So this is, if for free we could have these facilities, what would add up? So I left out the energy cost of making them. For most of these facilities, the energy cost is much smaller than the energy they will produce in their lifetime. So as a physicist, I'm happy making this approximation that I've left out the energy cost of making them, which was perhaps 5% or so of the energy that they'll generate in their life. That's not true for all technologies, however. Photovoltaic panels, at the moment with today's technology, are very energy intensive to make. So it's a very important question to ask. As for the solar power stations using concentrating solar power in deserts, I don't actually know what their energy cost is. And I think it's a good idea to carry on doing some research and development and see what will happen to the financial cost and the energy cost of making them.
I should have added, not to embarrass you, but just it would be great if you also just say who you are so David knows who you are and what your affiliation is. Next question, in the back there, please.
Hopefully there won't be any feedback. You mentioned that one thing that individuals could do to reduce their energy consumption was to become a vegetarian. And I would like to challenge that assumption. Now, I think that factory farming is indefensible and it is very energy intensive because of the use of grains. But if you grass feed animals, you are not only using less energy, and in fact you're using solar energy, but you are increasing the amount of topsoil that you're generating. Whereas if you are factory farming grains and soy, you're using an enormous amount of petrol in the form of fuel and fertilizer. Not only that, you are also depleting the soil and the topsoil. So you mentioned that Massachusetts does not have any deserts yet. Well, Iraq didn't used to be a desert. It used to be part of the Fertile Crescent, and it is now a desert because of excess grain agriculture.
Mm-hmm. Okay, so the question is, vegetarian or carnivore, what's better? And obviously it's complex and depends on the country and the geography and exactly how you feed the animals and so forth. But here's some numbers relating to energy consumption. The energy going into you, if you're an average human, is about 3 kilowatt hours per day. You could get that directly from plants. If you eat meat instead, then that queue of animals lining up waiting to be eaten by you have to have plants going into them. And it takes about 1,000 cow days to make a cow. And so the queue of animals that you live on is quite substantial and weighs quite a lot more than you do. And they're not 100% efficient at turning the energy in the plants into energy that gets into you. So you end up with a footprint that's quite a lot bigger. Something like 15 kilowatt hours per day is the chemical energy that is going into the mouths of the animals. Now, you say, no, that's not the full story. Absolutely, because real farming involves fertilizer, tractors, processing, and so forth, which also has an energy cost. So what I told you so far is just the energy going into the mouths of the animals. In terms of fertilizer costs, yes, it depends how you make your grain and how you make your vegetarian food. And if you're in a country like New Zealand or Wales, where you have very mountainous terrain and you can have sheep run around, maybe it's a good way to harvest that biomass. But the land requirement for the carnivore's lifestyle is indeed bigger. And in the future, in 2050, if we're serious about getting off fossil fuels, we really need to ask, where are we going to get our energy from? I talked about wind, nuclear, and solar in deserts. Another option is biomass. And there are many processes that we depend on with our modern lifestyle, such as industrial processes, chemical processes, flying, freight, international shipping, which run on fossil fuels at the moment. And to defossilize those, perhaps we need to be looking for some of them at biomass as a source. And so perhaps there's going to be a tension in land use in terms of wanting to get energy from land areas. And this map visualizes what you would need to do to get 5 kilowatt hours per day per person from wood in Britain, and that's shown by these green areas. And then for biofuels, this yellow box here is showing the contribution of 2 kilowatt hours per day per person from biofuels, which would be delivered by these yellow areas on the map in Scotland and all over England. This, remember, is just 5% of today's consumption of liquid fuels for transport. So I completely agree that agriculture is a complex thing, and that the choice between being a carnivore and a vegetarian is not a trivial one, but I think it's important to look very carefully at the numbers.
Another question over here.
Hi there. My name is Michael, and I'm an undergraduate at the college. My question is, for all your calculations, you've sort of taken data for current current technology, but you haven't factored in, any improvements that may occur. I was just curious, was that just because forecasting improvements is a very sketchy business, or I guess, what are your expectations in terms of efficiency improvements and cost improvements in these technologies?
Okay. How close are we to the limits of the laws of physics? Can these technologies get far better? Let's talk about wind first. This remarkable photograph visualizes the wake effect of one wind turbine on the other wind turbines in the wind farm. Windmills are already very close to the physical limit of what a disc-shaped energy extractor can deliver. The Betz limit says you can get about 59% out of the wind, and these are delivering about 50%. If you pack them closer together, you wouldn't do any better because the wake effects would get worse. So windmills are at the physical limit. You could make them taller and bigger, and then you'd get more power per turbine, but you'd have to space them further apart, so the power per unit area would stay much the same. It would just increase very slightly because of the increased wind speed. So I don't see a prospect for a massive improvement in the power per unit area, though the costs may come down, the financial costs, which I haven't talked about at all today. On the photovoltaic end of things, what could happen to photovoltaics? How close are they to the limits of physics? Well, standard photovoltaics today are single junction photovoltaics, and the physical limit for them is you can have, in principle, 31% efficiency at converting sunlight into electricity, and you can't do any better. That's the Shockley-Queisser limit. And they're already at an efficiency of 20% with today's photovoltaics, so remarkably close to that limit. So again, that's a technology I don't see getting much better in terms of the area required for it. In fact, I think what's going to happen is hopefully the costs are going to come way down because photovoltaics are still too expensive, and they'll come down along with a reduction in efficiency, I would expect, which will be okay. As long as they get much, much cheaper, we might be happy for the efficiency to drop down to 10% or so. So what I've tried to do in this work is indicate what the limits of the laws of physics are. In terms of technologies, I do hope there will be technological breakthroughs. I hope we'll come up with cheaper, smaller storage systems for storing electrical energy, lighter batteries and so forth, heat stores in buildings. I hope heat pumps are going to get more efficient. But I've tried to take a realistic view using today's technology and the limits of physics.
Yes, in the back here.
Hi, I'm Grace. I work with the Massachusetts Clean Energy Center, and I was wondering, as a tag along to that question, if you could speak about kind of the limits of physics for our grid infrastructure, and if something like smart grid might really drastically improve the system in general.
Okay, so could smart grids make a difference, and what are the limits of physics? The efficiency of transmission grids is actually pretty high. So in the British grid, only about 8% of the electricity generated is lost in the transmission infrastructure, and most of that is lost in the local grid. The long-distance grid loses only about 1% of the energy. So energy loss isn't really the concern for grids, but the smart grid, I do think, has a crucial role. There's the question of matching supply to demand. At the moment, we match supply to demand by having fossil fuel power stations switching on and off. That's our main mechanism. If we could have a smart grid in which demand is controlled in a smart way, that could lead to great savings in capital costs. We would need fewer generating stations, and they could just run flat out or at whatever rate they are naturally producing if we're talking about renewables. So I see the smart grid as a really crucial part of the 2050 vision. New pieces of demand that we're imagining might come along are electric vehicles and heat pumps for heating buildings that are not currently heated in that way. And both of those pieces of demand are not time critical at all. You don't care when your electric vehicle gets charged as long as it is ready to go at 8 in the morning. And you don't care when the heat is being pumped into your building either, as long as you're feeling comfortable. And so those are pieces of demand which are very large, and that could be moved in time very easily. So I see that as one of the main roles for the smart grid. The other contribution a smart grid will make is nothing to do with the laws of physics, but it's the laws of humanity, which is if the smart grid can somehow engage the user in understanding their meter readings and having more of a live feeling for what's going on day by day, then I think we could get massive behavior changes, because it is very easy after you've used the DVD to switch off the DVD player. And if we can get people to make that behavior change, then the savings from that and computers and laser printers and so forth are really substantial.
Yes, over here.
Thanks. My name's Murray. I'm a postdoc in applied physics. And I was curious on your comments on the recent climate scandal in the UK and what that's done. I'm speaking about the email releases. What that's done for this whole endeavor. And also if you can step out of your physicist shoes and maybe give us some recommendations for what public policy can do to accelerate some of this change.
Okay, let's take the first question about climate. Some people say that there's been a scandal. I don't think scandal is the right adjective for what's happened. Someone stole some emails and then published them, and a lot of mud is slung at these people, saying that they've done all sorts of bad things, but I don't actually see evidence for them manipulating data or anything like that. Nevertheless, that's what the mudslingers have been saying, that there's been wrongdoing, and it's caused a lot of damage, and I think mainly quite unfairly. And what I'd like to say about climate is I'd like to reflect on the way the science really works. I think the public impression is that climate science is all about looking at a graph of temperature versus time and arguing over the temperature versus time and coming up with some attribution of where did this temperature change come from, if you believe there has been a change, and is it getting colder during the last 2 years or not? And I think that's a travesty of what the science community are actually up to. The travesty says, oh, all they do is they look at this graph, then they look at this graph, which is the carbon dioxide concentrations for the last 1,000 years, and they say, oh, that went up too, therefore there's a link. But that's not what's actually going on. If it were like that, it would just be like the Pastafarian theory that says global temperatures have gone up and piracy has gone down, therefore we need more piracy. But the difference between the piracy theory of global warming and what real climate science is doing is that real climate science has got a mechanism. And the mechanism was recognized in 1827 and measured in 1860. And there's still uncertainties about all the feedbacks in the system, but they also make predictions that are far more complicated than just referring to a single number. It isn't all about a single global number, the temperature of the planet. In 1975 already, computer models were made that modeled the Earth as a two-dimensional object with a height of an atmosphere and a latitude replicated around the axis. So this is showing latitude and height. And they made predictions not just of a single global warming, but how much warming do you get everywhere when you look in different locations, look at radiative transfer using the known equations of physics, with heat flowing in at the equator and out at the poles. And these computer models made detailed predictions, more than just one number. These are the predictions if carbon dioxide concentrations were doubled. And the predictions include details like you get warming in the troposphere, near ground level, and you get cooling in the stratosphere. Plus, you get more warming at the poles than you get at medium latitudes. So the predictions are detailed, and they're testable, as long as humanity does the right thing and carries on emitting carbon dioxide so we can see what happens. And humanity's been doing a reasonable job. We haven't doubled carbon dioxide concentrations yet, but they've gone up enough that you can actually measure what has happened. And remember what I said, tropospheric warming, stratospheric cooling, that's what the data is showing from many independent experiments. And the predictions made prediction about temperature change at different latitudes as well. And here, now in the 2000s, you can do predictions in color. And the predictions take into account other effects in addition to greenhouse gases, which dominate in the predictions. The computer models based on physics predict, again, warming in the troposphere, more warming at the poles, cooling upstairs. And you can actually make observations, not over the whole planet, because we don't have a sufficient observation network, but here on the bottom right are the observations actually measured compared with the predictions of the latest computer models. And you can see the observations largely agree. There's warming in the troposphere. The tropopause has gone up a bit, and the cooling in the tropopause and in the stratosphere is occurring. Of course, the predictions aren't perfect. There's a little hole here and a place where some cooling is happening near ground level. Goodness me, call the media, quick. Predictions wrong, shock. Yes, the science still has uncertainties and these models are not perfect. But my feeling is the climate scientists are actually making detailed predictions and they're onto something.
We have time for one more question. Right here in the middle, please.
I am Carlos. I am in sabbatical semester here at Harvard. I wanted to tell first that pirates are coming back in Somalia, and the second thing is I wanted to ask if you are willing to make a guess about what will actually be the future of energy.
Okay. I'm being asked to make a guess about a future of energy, and I was asked earlier also to make policy recommendations. I think the policy recommendation I'd like to make, which will perhaps answer your question about the future, is I would really like the public to engage in a numerate conversation about our energy options, putting all the options on the table at once, so demand side and supply side options. So I've done a little bit of this in small groups where we take little cards that represent in green what you could get from various renewables, and you can slide the cards around to indicate how much you would get from renewables to match today's consumption. Then you're introduced to some red options which show today's consumption, and you can make lifestyle change and technology change assumptions about the red side. And then you can discuss how you would, as a group, like to agree with each other about what to do with your red stack and with your green stack. And by this sort of approach, I am hoping that humanity will choose a plan that adds up. And myself, I'd actually be content with any plan that adds up and that gets us off fossil fuels. So I don't want to recommend a particular outcome. And in my job in the Department of Energy and Climate Change, we've been developing a calculator, which could be a web-based model, a spreadsheet, that allows you to make choices on the demand side and on the supply side. So we have levels of action. Do you go for a lot of home insulation or not very much? Do you go for a hell of a lot of nuclear power corresponding to an Apollo mission's worth of nuclear power or none? What do you do about wind? Do you have an Apollo level of activity on wind or very little activity? And you can make all these different choices and then see what the outcomes are on the right-hand side in terms of greenhouse gas emissions. Do we reach our target, which is for Britain, an 80% reduction on 1990 levels by 2050? And we can have other outputs of economic measures, security of supply measures, and so forth, land area. What does the view from your window look like as you make these choices over here? And do we have a plan that adds up? So I'm hoping that every country will be able to make these sort of calculators and have public engagement processes that help people actually understand the choices we need to make.
So remember, Christina Johnson will be here on April 13th. Please come and join us then. Enjoy what I hope will be a wonderful spring weekend, and please join me in thanking David again for joining us.
Thank you very much.